Okay, so we have considered the effect of sampling, and we have specifically noted that whenever we sample a time domain signal, its effect in frequency domain is that the spectrum becomes periodic. And we have seen some argument, some mathematical argument that kind of justifies the reason why the spectrum has to become periodic, and that mathematical argument is described on this slide. But now let us understand this in a little more, with a little more depth. And so for that, we are going to go back to the definition of the Dirac delta function that we had looked at, we had studied some time ago. And if you recall, in that definition of Dirac delta function, we had specifically considered two different properties. One was sifting property and the other was shifting property. So the sifting property of the Dirac delta function says that this type of function can be used to sample any uh, any desired signal or any desired function in this case. And then there is another property which is called shifting property, which says that any function after convolution with a Dirac delta centered at x naught actually ends up shifting by x naught. And that is what we had seen by this particular example. So now actually we are going to consider the effect of sampling a signal by making use of both the sifting and shifting properties of the Dirac delta function. And so towards that, first of all, we will now consider a train of impulses, uh, which is defined like this. It is not just one impulse at t equal to 0, but it is in fact a sequence of impulses, actually infinity number of impulses, starting from n equal to minus infinity to plus infinity, and these impulses are t of s seconds apart in time domain. So this is a train of impulses, and the separation between impulses is t of s. Now, what is the Fourier transform of this signal? That is a question that we will now consider. So we will think of this train of sequences, this p of t, in two different manners. One is that we will say that p of t is discrete time, and that makes sense because p of t is defined only over n times ts seconds, where n is an integer. For all the other values of time, this p of t is 0. And so we are justified in calling it a discrete time waveform. And we have said that whenever a time domain signal is discretized in time, its frequency has to be periodic with a period of f of s hertz. So that is kind of the first observation that we will make. The other way of looking at p of t is that, no, fine, it is a continuous time signal except that it is periodic. Why? Because it is this one impulse which keeps on repeating every t of s seconds. So this signal, you can say that it is a continuous time signal with a period of t of s seconds. But there again, we have noted that whenever a time domain signal is periodic, its frequency domain has to have discretized frequencies. And so now we are having p of t, this p of t, which we are thinking of it in two different ways. One is that it is continuous in time but with a periodicity of t of s seconds, and the other is that it is discretized in time with a sample duration of t of s. But then what we end up finding is that capital P of f, the Fourier transform, also has to have the same two viewpoints. Either we can think of capital P of f as being periodic with a period of f of s hertz, or it is discretized in frequency with a frequency sampling of f of s hertz. Anyways, this is just an argument. Um, we are not going to go into the math, the detailed derivation uh, of the Fourier transform of p of t, but based on this, what we can possibly infer is that this small p of t and capital P of f, the time domain and the frequency domain, they may actually turn out to be having the same type of mathematical expression. And that, if we infer that from this argument, it wouldn't be entirely a wrong argument. So that is what is shown here, that if I take Fourier transform of small p of t, I get this capital P of f, and it also is a train of impulses, except now that train of impulses is separated by multiple of capital F of s. So here it was separated by capital T of s. And remember, capital F of s is inverse of capital T of s. So in both the cases, in the time domain we have an impulse train. In the frequency domain also we have impulse train. The difference is that as I keep on increasing this T of s, meaning I keep on making this separation between the impulses in the time domain bigger and bigger, the separation between the impulses in the frequency domain is becoming smaller and smaller, and vice versa. Okay, so this is our two equations which we are going to use now. P of t is an sequence of impulses, an infinitely long sequence of impulses where two consecutive impulses are separated by t of s seconds. And it turns out that when I take Fourier transform, the Fourier transform itself also is a sequence of impulses. These impulses are now located in frequency domain, not in time domain anymore. But it is still an infinitely long sequence of impulses whose impulses are separated by capital F of s hertz. We have not derived this relationship using all mathematical detail, but this is something that we are going to kind of use in our argument about the effect of sampling. Now recall the sifting property of Dirac delta, which says, oh, by the way, this is the Fourier, this is one another Fourier transform pair. The impulse train in the time domain has a Fourier transform which is also an impulse train in the frequency domain. Okay, so now consider the sampling in time domain. We have some continuous time signal that now we are going to call it s of t, and we are going to discretize the time. And the way we are going to discretize the time is by invoking the sifting property of Dirac delta, SIFT. And remember, the sifting property says that Dirac delta function can be used to sample a signal. And so that is what we have done here. We have simply taken s of t and we have multiplied it by p of t, this train of impulses, the sequence of impulses in time domain. And at the location of the impulse of this train, we will get the value of that function, value of this signal s of t. And at all other values of t, this discretized time signal will be 0, because this p of t is 0, and because we are multiplying s of t with p of t. So this is a mathematical representation of sampling operation in time domain. The discretized time signal, which I have denoted as s, and then on that I have put this wavy hat, we'll call it s tilde. So this s tilde is a function of n times ts. It is a function of discretized time. is nothing but the original continuous time signal after it is multiplied by p of t. Now let us take Fourier transform of this equation 1 on both the sides of this equality sign. So when I take Fourier transform of the left hand side, I obviously get the Fourier transform of the discretized time domain signal. But look what happens when I take Fourier transform of the right hand side. On the right hand side I have this multiplication going on. And we have seen this earlier, that whenever I multiply two signals in time domain, I get convolution in frequency domain. So my original spectrum, the spectrum of continuous time signal, is getting convolved with the spectrum of p of t, which is the impulse train in the frequency domain, where those impulses are separated by f of s hertz. Here this multiplier, this multiplication, the product operation with individual Dirac delta function that make up this p of t ends up giving this s tilde of n times ts, our time domain samples. But what do you think is happening over here on the right hand side of equation number 2? This capital P of f also is made up of Dirac delta functions, except those Dirac delta functions are shifted in frequency domain, and they are shifted by integer multiple of f of s. And for each integer multiple of f of s, there is a delta function. What happens when we convolve s of f with a particular shifted Dirac delta function? Again, we go back to the shifting property, which says that a convolution of a particular function with a Dirac delta shifted by some x naught ends up moving that function over at x naught. And so what happens is that this s of f gets moved to n times of capital Fs. But it doesn't get moved only one time. Actually, it gets moved there infinity number of times at each integer multiple of n times f of s, because this convolution is happening on each individual Dirac delta function inside this capital P of f. And so that is why this s of f becomes periodic in frequency domain. So let us see that. Let us say that s of t, small s of t, the time domain signal looks like this, and its spectrum looks like this with certain bandwidth b, meaning that s of f is 0 outside of this range. And now let us say that we take this s of t, continuous time signal, and multiply by p of t. And p of t is a train of impulses, and so we end up getting just the samples of s of t. And so that is what is shown over here, this diagram here. You see that I am just getting the samples of s of t because I multiply it by this periodic train of impulses. So this s tilde of nts is nothing but a sequence of such samples of s of t. But capital S tilde f, the Fourier transform of this sequence of samples, becomes the original spectrum S of f after it gets repeated by capital F of s hertz. So it becomes periodic now. And this is happening purely because of the shifting property of Dirac delta function. So this is a way of looking at the effect of sampling in time domain. It's another way of kind of proving to ourselves, and this is not a detailed mathematical proof in all the mathematical glory. We didn't go through some sequence of mathematical steps to show that the effect of time domain sampling is the periodicity in frequency domain. But we kind of got the concept behind such a proof. And this type of proof is completely different from this reasoning that we gave here to show why this signal should become periodic once we sample it in time domain, why its spectrum should become periodic. This is one argument. This is now a completely different argument which makes use of two different things, or actually three different things. Very first, it makes use of the sifting property of Dirac delta. Second, it makes use of a relation that the multiplication of two time domain signals is same as convolution of their spectra. And the third thing that it makes use of is the shifting property of Dirac delta function, because of which this S of f gets shifted to all the multiples of f of s. Minus f of s 0, plus f of s 2, 2 times f of s, 3 times f of s, all the way until infinity times f of s. And therefore the spectrum became periodic. Okay, so this is one more way of looking at another way of understanding why sampling in time domain would make the spectrum of the signal periodic in the frequency domain. The last thing that we will do before we conclude this video is known as the sampling theorem. Remember the sampling theorem that we had written over here, that a continuous time signal can be exactly recovered from its discrete time samples provided that the sampling rate is equal or greater than the bandwidth b of that signal. What this sampling theorem says is that suppose I have this s of t which is continuous in time. Actually, I can just store in my computer, or I can transmit over a wireless channel or wireline channel only these samples here which are shown by these impulses. I do not need any other intermediate values of this signal s of t at all. Even if I keep only these samples and if I throw away all these intermediate voltage values, I am still able to recover the original signal back completely without any change in the original continuous time signal s of t. Now if you think about it, that seems like kind of hard to believe. And how can you have this continuous time signal? You just pick some few samples of this signal, and then from that you recover the whole signal back entirely. So it seems like a little bit hard to believe, but it's a very crucial statement, because you know that it is impossible to store the continuous time signal in the computer. A continuous time signal is a real valued function of real valued time, and when we say real valued, we are talking about real numbers, and the real numbers need, even a single real number will take infinite memory. So forget about representing this continuous time signal in the computer or in your cell phone, which is essentially a computer. We cannot do that. But if we just consider the samples of this s of t, then now we are talking. The samples we can definitely store and we can process inside a computer, or maybe in your MATLAB or Python or C++. The problem is that what if we just keep the samples, throw away the rest of the continuous time information of S of t, and then what we get is not actually the original signal at all. It looks like some distorted version of S of t. That is where the sampling theorem steps in. And it tells us that if you are careful and in this sampling process, if you make sure that this f of s, capital F of s, which is the inverse of t of s, if you make sure that f of s is greater than this bandwidth b, then using these samples, you are not giving up anything. Storing these samples and processing these samples inside a digital computer is same as if you stored the entire analog signal and processed it. The question is, why is that the case? And the reason is that we know that after we sample, the spectrum of the signal becomes periodic. So the only difference between the continuous time signal and the discrete time signal, the only difference between the two in the frequency domain is that the continuous time signal has a frequency spectrum which is aperiodic. It has just one non-zero hump over here, whereas the same signal after sampling in time domain became periodic. The same hump got repeated f of s hertz apart. Now if f of s, capital F of s, is bigger than b, which is the requirement stated in the sampling theorem, then this different humps will not overlap with each other. They will be apart from each other. They will not touch each other. And so therefore, I can actually take this spectrum here, S of f, S tilde of f, capital S tilde of f, and I multiply it with a rectangular function in frequency domain. I multiply this S tilde of f in frequency domain with a rectangular pulse which is centered at 0 hertz and its width is b hertz, capital B hertz. Because of that, what will happen is that after that multiplication, all of these other replicas of this periodic S tilde of f will get wiped out. They will get zeroed out because that rectangular pulse is 0 there. And remember, I am doing multiplication in frequency domain. And so from this S tilde of f, I will recover S of f, which is this aperiodic signal with a single hump who is centered at 0 hertz. But that is same as my S of t in the time domain. So if sampling rate f of s is greater than b, it is possible to recover the spectrum of the continuous time signal from the spectrum of the discretized time signal. And the way to do that is multiply S of f by a rectangular pulse in frequency domain of width b hertz centered at 0 hertz. When we do that, it will remove all the replicas of the main spectrum and it will retain only the base of fundamental period, but that is exactly the original spectrum S of f. So we can say that we have recovered our original signal. So that is the frequency domain viewpoint. But remember, whenever we have a frequency domain viewpoint, we just apply the duality argument and we get the time domain viewpoint. What is the time domain viewpoint now? Multiply becomes convolution. Convolution of what with what? Well, convolution, well, this is a typo here, typing mistake. This should be S tilde of f. This one here. So convolution of in inverse Fourier transform of S tilde of f, which is nothing but S tilde of n times Ts. So we will convolve this sample train. We'll convolve it with what? We'll convolve it with the inverse Fourier transform of a rectangular pulse in frequency domain. What is the inverse Fourier transform of a rectangular pulse in frequency domain? It is one over here. It is a sinc function in time domain. And so if we take this sequence of samples in time domain and we convolve it with that sinc function in time domain, we will get the original CT signal S of t back. And there is a nice diagram of this operation in the textbook by Couch. So I suggest that you go and look at this diagram. So that is called the sampling theorem, and that allows us to appreciate the very first block of analog to digital conversion. Now, this is the argument made from a purely mathematical point of view. In reality, as we know, we cannot have an infinitely long sequence of Dirac delta impulses, because Dirac delta impulses themselves are not realizable. So practical sampling schemes, they look like this ideal sample train of Dirac delta function, but there's small differences. The impulses are replaced by thin pulses, and then how to do that sifting operation in time domain is another design aspect. And there are two ways. One is called natural sampling, another is called flat top sampling. And depending on whether you do natural or flat top, this convolution operation has a different effect. So please read the relevant portion of Couch's textbook to understand what is the natural versus what is the flat top sampling. Okay, we'll stop over here for the time being.